Hello and welcome back to Math Class in Session. Grade 11 Math, applications of exponential functions. So this is all about some word problems and how we solve when we do word problems. I would suggest that you watch the video with a pencil and a notebook handy and take basic notes. If you were a class of students, I'd say what goes on the board goes in your notes. So I'd suggest that you get the points of this video written down. At any rate, we'll do applications, word problems. Let's take a look. Exponential growth and decay. Some things in our world grow exponentially. Populations of cities, towns, countries, populations of things. Could be the moose in Algonquin Park. They grow exponentially. The number of bacteria in a petri dish, the number of dollars in a bank account. Well, there's a good idea. And the value of a vehicle decays exponentially as time passes. It follows one of those curves. We know the curve where it looks like the plane landing on the x-axis. That would be exponential decay, as opposed to exponential growth. Looks more like the population of the Earth. So if b, the base of the exponential function, is greater than 1, it's growth. The curve is going up. It's sloping up. It's taking off. And if b is less than 1, it's decay. It's sloping down. It's becoming asymptotic to the x-axis. We've studied this previously in the unit. But the new thing for this video is that there's not just a B, but there's an A. And A is associated with initial conditions. I'll show you what this means. This is a form. It's not a formula. The blinking cursor here is a form. That is going to be the form of our exponential equations. It's going to be a factor times a base raised to an exponent. A factor times a base raised to an exponent. So the factor, in this case A, is associated with initial conditions. So in our word problems, it will say things like a petri dish begins with 50 bacteria. So that would be code for A equals 50. Example 1. A bacteria dish begins with 25 bacteria. So it's a subtle hint. A is going to be 25. If the doubling period is 2 hours, how many bacteria are there after 10 hours? So we start with our basic form. It's not really a formula. It's n equals a factor times the base raised to the exponent t. So n equals ab to the t, where n is the number of bacteria in the dish. And we know that the initial conditions is 25. So we can put 25 in there for a. And we know that it doubles, according to the words in the problem here. The doubling period, it doubles in 2 hours. So when I make t a 2, I can make n double what the initial conditions were. So that would be 50. Dividing both sides by 25, we have b squared equals 2. So if I divide by 25, it vanishes here, and this becomes a 2, and I just turned it around. Taking square root both sides, and using a calculator, so I have the base of the exponential function, and I know the initial conditions to be 25. So here it is. Here's the form. A, B to the t. So it's A, the initial conditions, times B, the base, which we figured out, to the t. And t is going to be 10 hours, because the question is how many bacteria are there after 10 hours? And we use a calculator for this. There's 800 bacteria after 10 hours. Exponential decay. Y equals ab to the x with b less than 1. Some things decay. Values of things decay. A is still the initial amount, and B is, well, the base of the exponential function. It's called the decay rate. Example next. After 5 years, a $64,000 truck is worth just $20,971.52. So initially, it was originally worth $64,000, but as the years go by, the truck rusts and its value decays, and it decays to $20,971.52. What is the decay rate? In other words, the decay rate is the B value, the base of the exponential function. Well, to get it, we'll take our form and we'll plug into our form. The initial amount being 64,000, and the amount after 5 years, so that's why x becomes 5, the amount after 5 years is this number, given the value is 20,971.52 after 5 years. Plug it into the form and do the math and figure out B. I'll divide both sides by 64,000. I'll take a calculator and get that decimal. And then I'll take the fifth root of both sides. So that's how this is solved. We take the fifth root of both sides. When we take the fifth root of b to the fifth, we get b. And of course, we'll have to take the fifth root of the other side as well on a calculator. So b is 0.8. Now hit the space bar, pause the video, take your calculator, and go fifth root 0.32768. You might do that by going 0.32768 to the exponent, and then use brackets 1 over 5. And make sure that you come up with the 0.8. And so we have our b value. And b value is the base, and the base of the exponential function is 0.8. Some people call it the decay rate. I call it the base of the exponential function. The truck depreciates in value by 20% per year. Now this is because 0.8 is lower than the number 1. But it's only 0.2 less than the number 1. So the difference between 0.8 and 1 is 0.2. And turning that into a percent, that would be 20%. Y equals AB to the x. Now we're going to do some examples about rates of decay and growth. If population money, for example, increases in value by 12% per year, then the b, the base of the exponential function, is 1.12. That's because this is the reason why. It's 100% plus 12 makes 112, but this is a percent. So to turn it into a decimal, we have to call it 1.12, and that's the base of the exponential function. If you see a word problem that says something's growing by a certain percent per year, this is how you figure out the base. We'll say 100 plus that number, 12, and then move the decimal over, and we have our b value. Similarly for decay. If a population decreases, or say the value of a truck decreases by, let's say, 15% per year, then the b value is 0.85. The base of that exponential function that's taking away 15% per year is 0.85 for this reason. 100, take away the 15%, so it's 100 minus 15 is 85. Now 85, that's 85%, as a decimal is 0.85. Example next, the half-life of a substance is 4 hours. How much of the substance will remain after 12 hours? And 2 days. If there were, now here's some keywords, 64 grams at the start. Okay, so they're telling you what the A value is. There's our form. I'm using M for mass. That's our form, and we know that the initial conditions was 64, so A will be 64. Now it says half-life, So that's the amount of time it takes to cut in half. So the 64 gets cut in half to 32 when the t is actually 4 hours. And so we've subbed all this into our form, and now we have to solve this for b. We'll divide through by 64, and we'll say that b to the 4th equals 32 over 64, and that's 1/2. So b to the 4 equals 32 over 64. b to the 4 equals 1/2. And we'll take the 4th root of both sides. So we'll take the 4th root of 1/2. So that's the 4th root of 0.5. Do it on a calculator. And we have our b value. Now, we can plug that into our equation. We know the a value. They told us clearly here, 64 grams at the start. We figured out our b value, and now we can make this statement. The mass is 64, so this is a, b to the t. But t is 12 hours for I. So that's a calculator exercise. Do it. And we get the mass is 8 grams after 12 hours. And just another question here, 2 days. 2 days, after 2 days, that's 48 hours. So just put 48 in and do it again. After 48 hours, it has really decayed. Example next. A bacteria dish begins with 100 bacteria, so there's a message, A is 100. After 5 hours, there's 1,600 bacteria. Find the doubling period. Well, we need to shed as much light on this as we can. We know something, that there's 100 bacteria at the beginning, and then 5 hours later, there's 1,600. So using our form, there's our form. A factor times a base to an exponent, we can plug into it. So when the t is 5 hours, there becomes, the m value becomes 1,600 bacteria, and the a value is, we know, to be 100. So we just plug all that in. We have to solve for b. Divide by 100, so we'll have 16, and take the 5th root of both sides. Here I've written the 5th root of b to the 5th is b, and that must equal the 5th root of 16, which is 16 to the 1/5. On a calculator, hit the space bar and try it yourself. 1.7411. So we know the b value. So now we can write this. We know the a value, we know the b value, and so the question is find the doubling period. So now the 100 has to turn into 200. Plugging it in and then dividing through by 100, we have this. This is another form. It's a brand new form. It's the whole purpose of this video, is this new form. Well, actually the other form too. The two forms. Look at this form here. It's a number equals a number to an exponent. When you want to know what the exponent is, when you want to know what this exponent right here is, this t value, when a number equals, no other form is good. It can't be 2 equals 5 times that, or 2 plus x equals that. It has to be just a number equals a number to an exponent. That exponent is equal to, ta-da, drum roll please, I left this box waiting to fill the box. T equals this. Now this is a button on your calculator. There's a log button on calculators. I hope there's one on yours. They're on all scientific calculators. To get the t value in this form, whatever the exponent is, t is equal to log 2 over log 1.7411. And as a decimal, according to the calculator, that's 1.25. So the t value is 1.25 hours. It takes 1.25 or 1 1/4 hours to double.